On October 3, 2025, the solar system experienced one of its most extraordinary encounters in modern astronomical history. An interstellar object designated 3I Atlas passed within just 0.2 astronomical units of Mars, about 29 million kilometers, marking the closest recorded approach of any known extrasolar body to a planet equipped with a full suite of operational orbiters and rovers. It was a moment planetary scientists had dreamed of for decades. A visitor from another star system, skimming past a world under continuous robotic surveillance. At the time of its passage, the red planet was being observed by an unprecedented network of spacecraft. NASA's Mars Reconnaissance Orbiter, MRO, ESA's Mars Express, the UAE's Hope Orbiter, and China's Tianwen-1 were all in active service. On the surface, Perseverance and Curiosity maintained continuous imaging and atmospheric monitoring operations. Every instrument capable of night sky observation was tasked to participate in what could become a milestone in planetary science: the first cross-planetary observation of an interstellar comet. Mission teams recalibrated imaging schedules, reprogrammed exposure sequences, and issued last-minute corrections to tracking algorithms. Across continents and time zones, research teams braced for a narrow observational window lasting only a few days. Never before had an interstellar object presented such an opportunity. The geometry was ideal yet mercilessly brief. 3I Atlas crossed Mars's orbital plane at high velocity, moving faster than any local comet, its trajectory illuminated only intermittently by solar reflection. For a handful of nights, Mars's orbiters and rovers were perfectly positioned to capture data from multiple perspectives: surface, low orbit, and high orbit. But the speed, brightness, and angular separation from the sun made the task precarious. Each observation sequence was a gamble against timing and probability. The primary scientific goal was clear. Researchers sought to determine whether 3I Atlas was a conventional icy body, ejected from a distant star system, or something more exotic, a fragment of a disrupted planetesimal or even a failed protoplanet. By capturing spectra of its coma, scientists hoped to distinguish interstellar ice chemistry from that of local comets. The composition of volatiles such as carbon monoxide, carbon dioxide, and water ice could reveal the thermal and chemical environment in which it formed. The chance to analyze pristine material from beyond the sun's gravitational reach was scientifically priceless. Yet despite this global readiness, the only publicly confirmed detection came not from an orbiter, but from the Martian surface. Perseverance's Mastcam-Z captured a series of night sky exposures during October 3rd and 4th. Within those images, two independent analysts, Stefan Burns and Simon Stimson, identified a faint, diffuse glow consistent with the predicted position of 3I Atlas. Both worked separately, downloading the raw data from NASA's planetary data system and applying rigorous calibration techniques: dark frame subtraction, flat field correction, subpixel alignment, and noise reduction across dozens of 29-second exposures. By stacking and median filtering the data, they isolated a subtle feature: an elongated patch barely above background noise but statistically significant. The signal's astrometric position matched the object's expected coordinates to within half an arcsecond. Their work, published informally on X, formerly Twitter, and Blue Sky, became the foundation for the only open-source verification of 3I Atlas's Martian encounter. They included their calibration scripts, processing notes, and error margins, allowing other specialists to reproduce the detection. The image itself is unspectacular, a dim smear against the Martian starfield, but its implications are profound. It demonstrates that even in the absence of official releases, disciplined analysis of open data can reveal credible evidence of an interstellar body's passage. While Burns and Stimson's findings gained cautious recognition, official agencies remained silent. NASA, ESA, CNSA, and the UAE Space Agency all confirmed observation attempts but withheld data pending calibration. No raw images, spectra, or quick-look thumbnails appeared in public archives. The lack of transparency, coinciding with a partial U.S. government shutdown and routine data embargoes, fueled public speculation. Some commentators framed the silence as evidence of a cover-up. Scientists, however, offered a more prosaic explanation. Interplanetary imaging pipelines are not designed for high-speed, low-luminosity targets. Calibration can take weeks, sometimes months. One misplaced pixel correction or cosmic ray artifact could create false detections, and no mission was willing to risk releasing unverified results into the viral chaos of social media. That chaos arrived anyway. As word of the Perseverance signal spread, so did a wave of supposed alternate detections. On astronomy forums and social platforms, users shared cropped images from Mars rovers claiming to show bright streaks or glowing trails. The most widely circulated came from a Perseverance navcam frame dated October 3rd, featuring a razor-thin diagonal line interpreted as a comet. Planetary scientist Emily Lakdawala quickly debunked it. Running orbital data through JPL horizons, she found the streak's timing, angle, and motion matched Phobos, Mars's inner moon, during a long exposure. Within hours, the Interstellar trail story collapsed. A second viral claim, a short bright streak from an October 2nd Mastcam Z-frame, also failed scrutiny. Its angular velocity was 10 times greater than 3i Atlas's predicted rate, consistent with a passing dust mote or cosmic ray strike. These episodes reinforced a vital principle. In planetary imaging, every anomaly must undergo positional, temporal, and photometric verification before drawing conclusions. Meanwhile, Mars's orbiters executed their carefully planned sequences. MRO's high-rise camera, with its sub-meter resolution, was tasked to attempt the highest resolution imaging of an interstellar object ever attempted from another planet. ESA's Mars Express used its Omega spectrometer to scan for faint volatiles, while the Trace Gas Orbiter configured its Nomad and Cassis instruments to detect molecular emissions in the near-infrared. China's Tianwen-1 adjusted its imaging campaign to monitor dust scattering in the Martian upper atmosphere. The UAE's Hope Orbiter, operating from a higher, more stable orbit, contributed wide-field coverage for contextual imaging. Collectively, these instruments could have provided the most comprehensive multi-platform data set ever gathered on an interstellar body, if all went according to plan. But deep space observation rarely runs smoothly. Each orbiter operated without real-time tracking capability. Commands had to be uploaded hours in advance, based on continuously updated ephemerides that sometimes shifted by arc minutes each day. Any deviation in pointing accuracy could mean missing the target entirely. Moreover, bandwidth constraints within the deep space network forced prioritization of mission-critical telemetry over scientific imaging. As a result, even successful exposures could remain stored on board for days before downlink. The process was intricate, fragile, and heavily dependent on timing. By October 21st, orbital mechanics imposed another barrier. 3i Atlas entered superior conjunction, moving almost directly behind the Sun as seen from Earth. This alignment effectively blinded all ground-based and most space-based observatories for 6 weeks. Perihelion, occurring around October 29th, coincided with this observational blackout, ensuring that the comet's most dynamic phase, its potential fragmentation or outgassing peak, was unobservable from Earth. For planetary scientists, the silence was both predictable and frustrating. The cosmos had hidden its most crucial moment behind the Sun. Preliminary findings from spectroscopic modeling suggested intriguing deviations from expectations. Early data from ground-based telescopes prior to conjunction indicated strong carbon dioxide emissions but weak dicarbon bands, explaining the comet's lack of the classic green hue seen in most solar system comets. Some analysts hinted at elevated metal content, nickel and magnesium lines above baseline, but without confirmed Mars orbiter spectra, these remain speculative. The working consensus holds that 3i Atlas is a natural interstellar comet, volatile-rich but chemically distinct from typical Oort cloud bodies. Still, the scientific community faces deeper questions. How can a world with multiple orbiters fail to produce immediate high-quality data from a once-in-a-century event? The answer lies not in incompetence or secrecy, but in process. Interplanetary missions follow strict protocols. Each raw frame must undergo bias correction, dark subtraction, and geometric distortion calibration before release. Instruments optimized for static terrain struggle when tasked with tracking a fast-moving target across a wide field. The potential for false positives is immense. A single hot pixel or streak misinterpreted as fragmentation could distort conclusions for years. Agencies have learned, often painfully that slow accuracy is better than quick misinformation. As the blackout continues, attention shifts to remaining observers. The Soho-Lascaux C3 coronagraph continues scanning through late November, though its detection threshold limits visibility to comets of magnitude 9 or brighter. Only a major outburst could bring 3i Atlas into view. ESA's JUICE spacecraft, outbound near Jupiter, may attempt deep-field imaging in early November, depending on geometry and command schedule. No official attempt has been confirmed. By December, when elongation increases, Earth-based observatories will regain access, with large facilities like Keck, VLT, and Subaru, alongside skilled amateurs, ready to attempt recovery. Whether the comet will remain bright enough is uncertain. Regardless of final results, the passage of 3i Atlas serves as a stress test for planetary coordination. It revealed both the capabilities and the limitations of our interplanetary network. Despite decades of progress, communication lag, data bandwidth, and calibration protocols remain bottlenecks. The event underscores the need for automated rapid response systems, software pipelines capable of detecting and confirming transient phenomena across multiple platforms without manual intervention. Future missions may need adaptive imaging modes and shared open databases where preliminary detections can be verified collaboratively before rumor overtakes fact. Beyond operational lessons, the encounter reopens a philosophical dimension within modern astronomy. Interstellar objects challenge the assumption that our solar system is isolated. Each visitor, Oumuamua, Borisov, and now Atlas, reminds us that planetary systems are not closed boxes but participants in a galactic exchange of material. Their compositions, velocities, and isotopic fingerprints may reveal how common our building blocks truly are. The fact that a rock or ice fragment formed around another sun can drift across interstellar space and pass within sight of our robotic explorers is both humbling and instructive. Technological limits aside, the event also highlighted the growing importance of data ethics and transparency in space science. The public's hunger for immediate information contrasts sharply with the discipline's cautious verification processes. As data volumes increase, agencies face a dilemma: release quickly and risk error, or wait and face accusations of secrecy. The future likely belongs to hybrid models, AI-assisted validation pipelines capable of flagging credible detections within hours while preserving scientific rigor. The Perseverance signal, extracted not by institutions but by independent analysts, is itself a demonstration of citizen science's growing role in major discoveries. Artificial intelligence now plays a quiet but transformative role in planetary research. Machine learning algorithms trained on noise patterns, starfield alignment, and sensor artifacts are already being used to scan raw archives for transient events. In the next decade, AI could autonomously identify interstellar objects, predict observation windows, and even command spacecraft to retarget without waiting for Earth-based approval. If 3i Atlas had passed a decade later, it might have been tracked in real time by AI-driven systems capable of reacting faster than any human command chain. For now, the story remains unfinished. As of early October 7, 2025, the only publicly available detection of 3i Atlas remains the faint stacked image extracted from Perseverance's Mastcam Z-frames by independent analysts. No high-resolution orbital images, no definitive spectra, and no compositional breakdowns have been released. Yet that single faint signal, barely visible in the noise, stands as both a triumph of open science and a reminder of our technological fragility. In the age of interplanetary exploration, the cosmos continues to remind humanity that certainty is earned, not granted. The data from Mars orbiters may still emerge in coming months, after calibration and review. When it does, the findings could reshape our understanding of how star systems exchange material across the galaxy. If 3i Atlas proves chemically unique, it will offer a direct sample of alien chemistry, evidence of molecular diversity in planet formation. If it resembles known comets, the result is equally profound, suggesting that the processes shaping planets are universal, repeating themselves across light years. Whatever the outcome, the 2025 encounter of 3i Atlas has already fulfilled a deeper purpose. It forced humanity to look outward and inward simultaneously, to measure not just the comet's path, but our own readiness to capture the fleeting moments when cosmic history drifts within reach. It exposed the delicate choreography of machines orbiting another world, the patience of scientists balancing caution and curiosity, and the potential of citizens armed with open data to make meaningful discoveries. The next interstellar visitor will not wait for bureaucracy or bandwidth. It will arrive without warning, indifferent to human schedules. What we build between now and then, our systems, our collaborations, our trust in data, will determine whether we witness its passage as spectators or as prepared explorers. In the silence that followed October 3rd, one fact remains certain. The universe continues to send messages across the void. Whether through faint light on a Martian sensor or through the gaps in our data, it reminds us that discovery is never complete. Atlas may fade into darkness, but the questions it raised will continue to guide the next generation of planetary science. Questions about origins, process, and the thin boundary between observation and imagination.